All right, the last section of our class, 8.2. In 8.2, we learn about the law of cosines, kind of similar to the law of sines, except it doesn't have that annoying ambiguous case, so I think you'll end up liking this one a little bit more. Just like the law of sines, I want to show you a little bit about where it comes from, although I'll go over that pretty quickly because that's sort of optional material. I then want to show you how we can use our old area formula and the law of cosines to come up with a new area formula, and then we'll do some examples and we'll be done. So first, let's come up with the law of cosines. We're going to start out with this arbitrary triangle ABC. I'll call this angle A, in which case this side is A, this angle B, so this side is B, this angle C, so this side is C. I'm not assuming that anything is a 90-degree angle. This is just your arbitrary triangle. What I then want to do is apply some Sohcahtoa knowledge. However, that's problematic because I don't have a right triangle. So what I'm going to do is create a right triangle. And that's what you see in red here. I'm going to drop this perpendicular. Maybe I'll call this, I don't know, H for height. And that creates two right triangles for me, one whose base is shown over here in red, and another one whose base is shown over here in green. So the red length and the green length together make this side length B. Now that I have right triangles, I can start using Sohcahtoa. I'm going to use Sohcahtoa with this angle C. I'm going to look at both the sine of C and the cosine of C. So the sine of C, let's see, Sohcahtoa, it tells me that's opposite over hypotenuse. So opposite relative to this angle would be my height here, and my hypotenuse is A. So the sine of C is H over A. Or if I wanted to solve for H, I could multiply both sides of the equation by A and get that H is equal to A times the sine of C. Little trick that we've done a few times in this class. And then if I want to look at the cosine of C, I better give this adjacent side length a name. Maybe I'll call it D. Again, using Sohcahtoa, the cosine of C would be equal to adjacent over hypotenuse, so D over A. And so if I wanted to solve for D, I could multiply both sides of this equation by A and get that D is equal to A times the cosine of C. What I want to do now is use my Pythagorean theorem. Informally speaking, a squared plus b squared equals c squared. But be careful, it's not this a, this b, and this c, because that only applies when I have a right triangle. Which right triangle do I want to look at? Well, I've already kind of exploited the one in red, so maybe I can look at the right triangle that has this base here in green. For this green right triangle, the length of this side squared plus the length of this side squared must be equal to this side squared. What's the length of this side here? Well, I haven't figured that out yet, right? You're like, it's b. No, b is the distance from here all the way over to here. Oh, right, it's b after you get rid of the stuff in red here. It's b minus d. That's true, and I know that d is a times the cosine of c. So this length in green right here is the entire length of the base of this blue triangle, b, minus the length of the base of this red triangle, d, which I figured out was a times the cosine of c. And then remember that h is equal to a times the sine of c, so I could say that this squared plus this squared must be equal to this squared. And that gives me something that's equivalent to my law of cosines, which is kind of cool. I mean, remember the big goal here is I wanted to relate together a's, b's, and c's, and maybe some trig functions about arbitrary triangles like the triangle ABC here. And now I have a formula that does just that. It's not the prettiest formula in the world. You can clean it up a little bit. So all I'm going to do is clean up this formula so it's in a form that's easier for me to remember and a little bit more useful for me to use. How am I going to do that? Well, let's first get rid of the parentheses. If I square these parentheses, there's two terms in here, so you have to think FOIL. This thing times this thing. Well, the b times the b gives me a b squared. The b times negative a cosine of c gives me negative ab cosine of c, and there'd be two of those things for the o and the I in FOIL. So I get minus 2ab cosine c. And then the last terms would be the product of negative a cosine of c and negative a cosine of c. The negative times a negative gives a positive, and I get a squared cosine squared c. And then over here, I got a squared sine squared c. Easy enough to get rid of these parentheses because there's just one term in here, so the exponent just kind of hits the two different factors in that term, and that's all equal to c squared. If you're really clever, you might notice that you have a sine squared plus cosine squared hidden in here. If you factor out an a from each of these two terms, you can rewrite this equation this way, but the nice thing about these parentheses is they're just equal to 1, because sine squared plus cosine squared for any angle is always equal to 1. So I got a squared times 1, in other words, just a squared. Rearranging some terms just to make things a little bit prettier, I get a squared for this a squared times 1, plus b squared for this one, minus 2ab cosine c is equal to the other side of the equation, which is just c squared. This is what's called your law of cosines. Much like the law of sines, it's a handy way to relate together the lengths of sides of a triangle and an angle in that triangle. And much like the law of cosines, it's not dependent on this triangle being a right triangle. In fact, in the special case that this is a right triangle, if capital C is a right angle here, then the cosine of 90 degrees is just equal to 0. So negative 2ab times 0, this is all 0, this would all go away. and I would just be left with a squared plus b squared equals c squared in the case that capital C is 90 degrees. Well, if capital C were 90 degrees, it's definitely not here, but if it were, then little c would be the hypotenuse. Really, our familiar Pythagorean theorem is just a special case of the law of cosines where capital C is equal to 90 degrees. You could even use that to help you remember the law of cosines. It's almost a squared plus b squared equals c squared, but because c is not the hypotenuse, we need this extra factor in here to adjust for the different lengths of the legs of the triangle. It's worth pointing out that all the steps of logic that I did to come up with this formula would be the exact same if I switched around these letters. Like maybe I called this A, and I called this C, and I called this B, for example. If I shuffle these different letters, I will end up with a formula that looks a lot like this, except these letters will be shuffled. There's really 3 different versions of the law of cosines. I could start with a squared plus b squared equals c squared and then come up with this term. I could also start with a squared plus c squared equals b squared and then come up with this term in between here. But be careful, this term here is 2 times whatever this letter is times whatever this letter is. So in this case, it would be negative 2ac. And then it's times the cosine of the capital of this letter, so cosine b in this case. I could have the c squared over on this side of the equation, I could have the b squared over on this side of the equation, or I could have the a squared over on this side of the equation. If the a squared is over on this side of the equation, then I'm left with b's and c's to be over on this side of the equation, and my term to make everything balance would be negative 2 times this letter, so negative 2bc, times the cosine of the capital of this letter, capital A. I got a little bit weird there. There it is, a little bit neater. The point is there's 3 versions of the law of cosines, and you can kind of think about it like you're memorizing 3 different formulas if you want. For what it's worth, what I do is I just memorize one version of the formula, and then I recognize how I can change this into the other versions by switching the A's, the B's, and the C's. For most people, the A's, the B's, and the C's are the easiest part. It's this part that people mess up. Remember, it's always negative. It's always going to be 2 times something, and that something will be the product of these 2 letters times the cosine of the capital of this letter. In the next video, I'll show you some examples of how you can use this thing. I think you'll end up liking how you use this thing. But before I end this video, I want to remind you of our area formula. Back in 8.1, we used the fact that we could figure out the area of a triangle, it's 1/2 AB sine C, to come up with the law of sines. It turns out that with this area formula and the law of cosines, if I took this expression and I solved it for cosine of capital C, and then used the Pythagorean identity, and I don't know, about 5 minutes worth of algebra moving terms around, what I could do is I could change this into something that's known as Heron's formula, a different way you can express the area of a triangle. And it's equal to S times S minus A times S minus B times S minus C. And you're like, oh, okay, that's not too bad. It's S, and then the A and the B and the C all have to get subtracted from S. I multiply those all together, and I take the square root of that thing. I think I can remember that. But wait, what's S? S is what's called the semi-perimeter. The perimeter is just the distance all the way around the triangle. So the perimeter is A plus B plus C. The semi-perimeter is just half of that. So it's A plus B plus C divided by 2. So for example, in this triangle here, suppose this side length is 4, this side length is 5, and this side length is 7. We have no other information. We don't know any of the angle measures. You're like, how could I possibly figure out the area? Because my area formula involves one of the angle measures. Well, thanks to Heron's formula, you don't need it. If you know all 3 side lengths, you could first figure out what S is equal to. S, the semi-perimeter, is the distance all the way around the outside, divided by 2. So 4 plus 5 is 9, plus 7 more is 16. 16 divided by 2 is just equal to 8. And I can use that to figure out the area. The area is just the square root of S, which is 8, times S minus A. I don't know, maybe we'll call this one A. So 8 minus 4, which is just 4, times S minus B. If we call this guy B, 8 minus 5 is just equal to 3, times S minus C. I guess if we've called this A and B, we're forced to call this C, and 8 minus 7 is just equal to 1. If I multiply together 8 times 4 times 3 times 1, I get 96, I believe. So the area of this triangle would be the square root of 96. And since 96 is 16 times 6, I could say that this is the square root of 16 times the square root of 6. So I can call this 4 root 6 if I'm really into simplifying these radicals. You don't need to be able to do that. I just want to point out that we could figure out the area of a triangle if all we know are the side lengths, and the square root of 96 would be a perfectly sufficient answer. Note, this is not the law of cosines. I didn't use the law of cosines here. This is what's called Heron's formula. Probably should have capitalized this person's name. And the only reason I presented it in this section is because it's derived from the law of cosines. I didn't show you that derivation. I think it's kind of boring, and I thought that I was testing the limits of your patience by showing you the derivation of the law of cosines. But trust me, the law of cosines and our old area formula produces this formula for the area of a triangle. And so because this is a consequence of the law of cosines, it's typically taught with the law of cosines. This is, I don't know, 10% of this section, and using the law of cosines is 90% of this section. So what I'm going to do is make a couple more videos that show examples of how to use the law of cosines.